Figure 1 of the common collector amplifier circuit in notes 14. What does the circuit look like? Voltage divider. And then transistor circuit. But you see how we do not have a collector resistor? No collector resistor. Instead, it's connected right away to VCC there. Okay? That's what's different about it. We do have an RE, and the output is connected not at the collector, but at the emitter through a capacitor C out, and that's V out. Okay? V in is with the capacitor C in. So here's my signal coming in. Here's my signal coming out. Okay? Note 1. The common collector amplifier is sometimes referred to as an emitter follower. What does that mean? That it ends up as a second stage of a two-stage amplifier circuit where it follows the emitter, common emitter circuit. That's why it's called an emitter follower circuit. Okay. It exhibits a high input resistance, so that whole circuit, if to the input signal, when the input signal sees this big circuit, it feels like a big resistor, okay, high resistance. It has a gain of about 1 or just under 1. So there is no gain. What comes in comes out, okay? So if the input is 200 millivolts, we get 199 millivolts. That kind of thing, okay? So input and output are about the same. Because of the high input resistance, it's sometimes called a buffer circuit. Buffer circuits, typically in amplifier circuits, mean just that. What is input becomes output. The input is capacitively coupled, so you've got C in at the base. You can see that it's connected to the base through the capacitor. The output is capacitively coupled to the emitter. So we've got the emitter, and we've got the output capacitively coupled to that. The output signal is in phase with the input signal. So when the input signal goes up, the output signal goes up. That's always the case at the emitter. It's only at the collector that when the input goes up, the output goes down. But at the emitter, the two signals are in phase. So you can see a picture in figure 1. The input signal is a sine wave. The output signal is a sine wave. Can you write a little note beside V out there, V out here, that it is approximately equal to V in, like this? The collector is at an AC ground, so as far as the AC signal is concerned, that VCC appears like a ground, and we talked about this last class. That to an AC signal, the VCC appears like at ground potential. So let us now go to nodes. Oh, before we go to node 14, let's go to page 4. Let's go to page 4. Page 4, example. So in that example, we see a common collector amplifier circuit, R1, R2, RE, and there is a load, RL, connected to the capacitor, and we're going to make that load to be an 8-ohm speaker, okay? The thing with this circuit is that if we do the DC analysis, see where it says stiffness test? Can you write down a note on page 4, not stiff? Can you write down not stiff on page 4 of notes 14? The circuit is not stiff. If you do that calculation of HFE times RE greater than 10 times R2, it is not stiff. Let's see. R1 is how much in this circuit? 10K. R2 is how much? 22K. RE is how much? 100. HFE is how much? 175. Okay. RL is how much? Right here. 8 ohms. So, as far as the stiffness test is concerned, number 3, HFE times RE, is it greater than 10 times R2? This is what we talked about, that as far as the voltage divider circuit is concerned, the voltage right at the division would be approximately equal to the regular voltage divider formula if the load is big. How big? 10 times R2. So our 10 times R2 is 10 times 22K, which is how much? 220K. So let's see if HFE times RE is 10 times R2 or not. HFE 175. RE 100. What's 100 times 175? Is it 17.5K? Is 17.5K greater than 220K? No. So the circuit is not stiff. Okay? Not to despair. If the circuit is not stiff, let's go to page 2. Page 2. We have a table in the middle of page 2. On the left side, the equations say stiff. On the right side, the equations say what? Not stiff. Page 2. So we can do the analysis using the not stiff equations. Okay? But it's so much easier to design an amplifier circuit, to troubleshoot an amplifier circuit, if it's stiff. And it doesn't take a lot of intelligence or a lot of smarts or a lot of analysis to make it a stiff circuit. One way of making it a stiff circuit is by doing what we do in notes 14b.